So what I'm going to talk about today is some of our work in higher order dependencies in network. And this was a work largely done by my PhD student, as all PhD students do, Jian Xu, who's now off at Citadel doing hedge fund securities using higher order networks. So that's the social good part of the work. So what sort of I'm going to talk about today is give an intuition behind what higher order networks are and what are the limitations on the ways we today may construct networks. The assumptions that we may apply towards the first order Markovian assumptions that we may apply, etc., and how complex systems largely come with varying orders of dependencies, and it doesn't matter what kind of complex system one is working with, a large variety of them do come with those varying orders of dependencies. So if we sort of look at this series, if you think about the raw data may come in as a pairwise, as weighted pairwise, as directed pairwise, with some temporal, with some matrix, with some tensor framework, and we can represent them as either heterogeneous network, temporal networks, directed, weighted, or simple networks as well. But if there are higher order dependencies that may be happening, imagine sequence of events. Imagine if you're searching for something on a website, you go from one click to another click to another click until you actually reach a destination. You reach the final endpoint, not because where you were just a point before, but you started your trajectory or your sequence from another point. So that sort of is the framework of higher order networks, is how do we begin to represent these raw sequences or trajectories of data with a network which accurately and correctly represents those dependencies. The dependencies that would be missed by our traditional way of looking at networks, where we assume things are first order, where we assume a Markovian order, first order Markovian order with them. So just sort of give you an idea as to what it is, so if you think about the world shipping network, so a ship may leave from Shanghai to Singapore to Los Angeles, and collectively, as these ships move across different trajectories, they form the higher order network. It's not where the ship is leaving from Shanghai to Singapore, it's left from Shanghai, Singapore to San Francisco, and that's what makes the trajectory of that ship. And why it's important? It's important for us to understand that, because if you're trying to model how invasive species spread in the world, it's not that the ship just came from Singapore to San Francisco. It's because the ship left a port, let's say in Shanghai, to Singapore, to San Francisco, and a species that may have been captured in the ballast of the ship in Shanghai may pose a risk to the port in San Francisco, for example. So those are some of the aspects that we have to think about. So if you look at it, if we go through a series of steps of the ship movement traffic, where as the ships move through different ports, and then they land then the ultimate destination is different. And if we were to construct the first order network about them, we would basically say that Shanghai, Singapore, Singapore, LA, Singapore, Seattle, Tokyo, Singapore, and Singapore, LA. Each of these ports, as the ships move between any of these ports, they have an equal probability of moving. It doesn't matter whether the ship that may have left Tokyo, and if it goes to Singapore, is more likely to go to Seattle versus LA. So what happens at an intermediary port is missed. That there's a likelihood of the ship going from Tokyo to Seattle is higher if it goes via Singapore, for example, or if it's higher if it goes via or from Shanghai to Singapore is higher when it goes to LA or Seattle, for example. So how we sort of propose to do is we propose to break it down by looking at these. If we consider these first order construction here, we propose to break it down as to how do we now begin to take these trajectories and say perhaps Singapore could be broken down into two nodes, because the likelihood of movement from Tokyo to Seattle is different, or from Shanghai to LA is different based on whether the ship came when the ship leaves Singapore, whether it left Shanghai or Tokyo. So what we are sort of essentially trying to do is we are trying to look for a framework to derive what the raw data from the complex systems may be. And then once we have sort of derived those raw data, such as the sequence of ships, the time they left a port, where they went to, and what kind of cargo they were carrying, for example, that is the raw data that was given to us. And if I were to just construct a network using the pairwise interactions, that from Singapore to Seattle, that's one node, and then or Shanghai to Singapore is one node, then I'm going to miss that the likelihood of going to Seattle is higher if the ship actually came from Tokyo to Singapore and the likelihood of going to LA is higher if it came from Shanghai to Singapore. That important trajectory, that important step will be missed if we just consider the first order interactions. So what we sort of started to think of doing is, can we first develop, so that's the raw data of interactions that exist. Now the question that becomes is, if we are interested in taking this raw data, which didn't come to us as networks, it was simply a ship movement traffic. The clickstream data that we may be looking at doesn't really come to us as networks. It comes as somebody's movement patterns on page A to page B to page C to page D, and how that trajectory happens. The social media, the information, the way it diffuses, the flow of dynamics to a social media is just not from A to B. It may have sort of traveled through a sequence of steps. How do we really begin to take that data where there are this longer term memory, where there are these longer orders of higher orders of dependencies, and incorporate those? So that was one thing so those are some of the challenges. How do we begin to represent the network correctly? And then once we represent the network correctly, does that mean that we now have to develop new algorithms for page rank or community detection or link prediction? Or can we come up with a network representation that will be agnostic to the raw data of interactions, that will figure out whether there is a higher order, and if there is a higher order, if there is a variable order? Because it could be between two nodes or between 2 points, 2 nodes in a graph. It could be a first order, the same system. It could be between 2 nodes, there could be a third order. It could be between 2 nodes, there could be a fourth order. So there are these variable orders that exist for dependencies in this complex system, so we really cannot make an assumption about what kind of dependency there may be. So A, can it be agnostic to the kinds of dependencies that may exist in the data? And B, if we can develop that network representation, can we leverage the existing network analysis tools or the existing algorithms to work directly on this kind of a network? And then finally, what we asked was, because we have now higher orders, what's the visualization framework to it? How do we interact with these? How do we simulate different scenarios? And the reason being is we were trying to apply this for invasive species management, and some of the policymakers said, that's great. Now you can tell me what port is actually ship leaving what port is going to pose a risk to what other port, but how do I interact with it? How do I visualize these scenarios? How do I sort of make an impact on the policy? And how do we begin to integrate the true heterogeneity of data, which could be economic trade patterns data, which could be ecosystem data, which could be how the climate data, how similar some of the ports are in the variables. How do we begin to integrate all of that? So that sort of is what we are trying to do here. So if we go back to the first order network that we were talking about, and if we look at the graph, if you look at the couple of trajectories over here from Shanghai, Singapore, LA, or Tokyo, Singapore, Seattle, etc., what we find is, just looking at these trajectories on the left, what we see is there's a higher likelihood of Singapore to LA if the ship actually came from Shanghai. There's a higher likelihood, and that's the actual data that we collected from the Lloyd's Maritime Insurance Unit shipping data. There's a higher likelihood of going to Seattle if the ship came from Tokyo. And if I just looked at it as a first order, I would be completely missing that relationship. I would be missing that relationship because it would tell me, doesn't matter where the ship came from, Singapore, LA, Singapore, Seattle is all equally likely. But that's not the case. And it's important to look at, and the same thing applies even when we're talking about information diffusion or flow of dynamics, is who tells you what matters on how you communicate it further. It doesn't, so your communication to another person is just not that dyadic. It depends where it may have come from as well. Who is that influencer? So those aspects come to play, which are missed with the first order representation that we may have. So we are not the first ones to sort of think about the higher order network. Roosevelt et al. In their Nature Communications paper in 2014 sort of looked at a problem and modeled this. They went up to the second order networks from that. So they basically looked at, and this is data from their paper, they looked at New York, Chicago, New York, Chicago, San Francisco, and they were looking at itineraries and the tickets, and then they extracted networks. And then what they found was that they used memory nodes to capture one more previous step. So they were able to capture second order dependencies in the data, quite accurately so. And in capturing those second order dependencies, they showed that the first order, traditional ways of just looking at network using the first order Markovian principles were grossly insufficient. So they achieved the second order dependencies, and then we sort of asked is, how do we go beyond the second order? And in their paper, they talk about higher order Markov models, while of course doable, are extremely complex due to the combinatorial explosion that may exist as a result of those. So they sort of, talked about this, and then they sort of stopped there. So in our research, what we are focused on is not just higher order, but variable order, which means if it's only a first order that exists, so be it. If it's a second order, we capture that. If it's third, fourth, or fifth order, we capture that. And how do we sort of scale beyond these things? How do we sort of even develop a parameter-free framework to create these dependencies? So sort of an example of variable orders could be, here's one where I leave Shanghai to Singapore, and then Singapore onwards, and then I may leave Tokyo. Tokyo is conditioned on Singapore given Tokyo, and Singapore could be conditioned on, which is where we're going to second or third order now, Tokyo, Busan, Tianjin. Singapore conditioned on, and Tokyo is conditioned on Busan and Dalian, for example. So they are these higher range of, so that's a higher memory that may need to be incorporated when we construct networks. So how do we sort of go about constructing this is, we look at the sequential data, which is the raw data given to us. It doesn't matter what the raw data is. We've applied this to cell phone communication data. We have applied this to shipping network data. We have applied this to website traffic data. We have applied this to human trafficking data as well now, as well as arms trafficking in collaboration with the Army Research Lab, because that's what happens, because folks are moving around different places until they land at one place. So everything else is sort of a made-up intermediary port, intermediary stopping point. So how do we capture those? Because if we just look at the last one to where the human trafficking actually happened, we'll miss what the route was from that perspective. So how do we sort of begin to capture those from that framework? So we take that kind of raw data, and then we sort of go through it in an automated way to understand which nodes may be most appropriate to split into the higher order nodes. Think about the Singapore example. Singapore was split into Singapore given Tokyo, Singapore given Shanghai. And Singapore given Shanghai, higher likelihood for LA. Singapore given Tokyo, higher likelihood for Seattle. So think about that's the kind of a split that we are conceptualizing here. And then what we go about is then we sort of go through the network wiring. So once we have we create and and then we rewire the network to go through this, and then we sort of develop a network representation, a data structure, if you will, which you can use with your favorite community detection algorithm, your favorite page rank algorithm. Nothing has to change from your analysis framework. So those were some of the aspects that we wanted to make sure that we have incorporated in the work. So I'll quickly pace you through some of the steps as how we may go about. So we sort of start with is the sequential data. So that's the data given to us, and then we count subsequences of various orders. That, how the traffic is coming, and we sort of go through that counting framework, and then we create a probability distribution for the first order. And then similarly we create probability distribution for the second order, and we create what the extended source node and target nodes may be. And then we sort of look at what the divergence between these distributions is and whether it sort of meets the statistical significance level. And then we go around converting all the first order rules into edges. And then we rewire the edges. So these were the first order rules that we had, that we first constructed, for example here. And then we construct the second order. And if the second order persists over the first order, we rewire the network to get rid of that first order from Shanghai to Singapore, and we sort of incorporate it fold it into a second order network. And we keep doing it. Then from a second order, we go back a step again, and we look at a third order. If that meets the criteria set by the algorithm for a higher order dependency, we incorporate that, and we fold the second order into a third order. And we keep doing it until we reach where we don't have a statistical significance or a confidence in incorporating beyond the previous order. So we keep going through that step. And then, of course, the question that does come to being is that if we do all this stuff, how does it scale? So we sort of go through this is the global shipping. Let me tell you a little bit about the global shipping data that we used. So we have access to Lloyd's Maritime Insurance Unit for the last 15 years. Every ship that's left every port in the world, what time it left, what kind of a ship it was, and what kind of a cargo it carried. So over the period of 15 years, we have the exact data, the timestamp, the location, the type, and the kind of cargo. And the reason we collected that data was because we were interested in looking at how species move around in the world. Within the US, the invasive species are $120 billion loss because of, even in the Great Lakes where Notre Dame is, not quite by the Great Lake, but still by the Great Lakes, where Notre Dame is. So we sort of see the zebra mussel, the Asian carp, etc. So how do we now begin to see how these species moved around? And the species moved around because of the shipping traffic. So we wanted to be able to model that shipping traffic to be more predictive about movement of these species, where the ship was a vector. So that's how we started doing this work, and that's when we realized that just looking at the first order was insufficient, and we had to look beyond the first order to truly capture the risk of one port to another port. So that's the kind of shipping data we had. And then and of course, as one can imagine, the number of edges would increase as we go about with the higher order. It goes from 31 to 85,000. The number of nodes increases as well, and the network density increases as well. And then we'll talk about the clustering coefficient, time, and the ranking, and you would see it actually scales very nicely irrespective of the time. So when we first came up with the version, this was a paper that we had published in Science Advances. We still had a critique of our own work was that it was heavily parameter dependent, where the user had to decide what kind of a confidence or support that needed to be provided. And it also had the complexity of space because we had these large graphs that were created as a result of these higher orders. So how do we sort of address those issues and take away the parameter dependence on the user? So since then, so the next version that we have now, which is now under review at ICDM, is we sort of looked at how do we now we address the storage issues as well as the order issues and the raw data size issue, and we bring it down to the complexity of just by order by raw data size. And the way we go about doing it is we compute the KL divergence, we pre-compute the KL divergence, and decide if the higher order will make a significant difference. So it does not have to go through all the possibilities for higher orders. There's actually a predetermined pruning step that's computed upfront, a priori, within the algorithm. So I'm going to quickly go through, I have about 10 minutes, 20 minutes? Oh, lovely. Oh, then I won't quickly go through. I'll go through some of the results on this work. So let's look at, for example, the influence on dynamics by looking at the higher order network. So if I'm given this ship traffic, BA, 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 etc., and I create, so these are the A, B, C are the three ports, and the ships are moving between the ports, and these ships create the network. The ports by themselves don't create the network. It's the ship that's moving or visiting one port to the other is creating the shipping network, if you will. So if we look at a first order network, given this three ship trajectory data, if I'm given that, I would create a first order network where I would say, all right, A goes to B goes to A goes to C goes to A. That's the network I would construct if I just rely on my first order framework here. The higher order network would say, okay, A goes to B, and B, A to B, the conditional is then A to B conditional, then that sort of cycles to B. And A goes to C, and A to C conditional cycles to C as well then. So that sort of is the first order network. And now if that's the testing set that's given to us, that can we predict these next steps that are going to happen if you're predicting about the dynamics of the network, where the movements may be, where the next location may be. So the first order network would be incorrect in CAB, would predict CAB, would not predict CAC, because that information is not captured in the first order network. The higher order network here, which is the second order here, which would also be captured by the second order Markovian work that Roswell and et al. Did, would capture the CAC prediction as well. So just, I hope this little illustration sort of gets to the point of where when we represent a simple three-port three node information, a network that's formed by ship movement, or network that's formed by our communications with each other, what have you. Even as individuals, we only connected if there's an interaction, right? So we look at those interactions and we form a network. The first order would be limited based on what it has, based on how it captures those dyads. The higher order is able to incorporate a memory in it, right? So how do we now, and as a result, if the next sequence is given for testing from a dynamics perspective, it's more accurate from a higher order network than it would be from a first order. And we sort of simulated a wide variety of movements, and we sort of went through 3 steps, 2 steps, 5 steps, and we looked at the accuracy of these things. And through all the simulations that we did, we were able to capture a much more accurate representation of the raw data. And because this was a simulated, artificially created data where we knew what dependencies existed. So we simulated various dependencies and threw it to the different kinds of network representation, and we were able to capture more accurately what's happening with the higher order than we could with the second order. So the kinds of higher order dependencies that were revealed by higher order network. So we looked at ship movement, about 3 million nodes. We looked at clickstream, about 3 million records, and as well as a retweet data of about 23.7 million. So what we found with the ship movement was up to the 5th order, and similar. While no one else has quite looked at the shipping traffic from this perspective, so we don't have a ground-truthted observation as to what may be a correct higher order, so we really don't have any other similar observations. But what we found on the shipping data that we had from the Lloyd's Maritime Insurance Unit, it went to about 5th order of dependencies. From the clickstream, we observed up to 3rd order of dependency. When we say up to 3rd order, which means that certain nodes or certain components of the system demonstrated 1st or 2nd order, and not all demonstrated 3rd order. So we are not sort of prefixing what the order may be, and now because we are parameter free as well, now we are able to naturally scale and discover what the right dependency would be in the data. And up to the 3rd order observation was sort of shared by other work which was published in 2012, where they sort of said that the Yahoo browsing behavior appeared to saturate at k equal to 3. And they looked at it from, again, a Markov chain perspective. And then from a retweet, because we did not have the original sort of where the followers came from, where they tweeted, so we didn't quite have higher dependencies that we could develop from here, but we were able to confirm some of the findings from Roosevelt et al. By simulating those scenarios within the retweet. So again, so mostly, most of the current approaches, either they ignore higher orders in the network representation, or they modify existing algorithms in recognition of that there is higher order dependencies in the network. Let's build an algorithm for link prediction. Let's build an algorithm to discover certain organization principles. Let's build an algorithm for clustering such that those higher order dependencies could be captured by the algorithm. So what we are sort of trying to do here is, irrespective of the two aspects, let's not ignore the higher order, and let's not reinvent the wheel. Let's come up with a network representation that can capture various aspects of raw sequence data, and also work with the existing algorithms. And I'm going to now sort of walk you through some of the works of using the existing algorithms and the kinds of observations we had. So just to give you an example here on how we are sort of able to make it happen with the higher order network without breaking the algorithm, is all we are doing is we are adding another node which is capturing the conditional dependency from Singapore to Tokyo to LA, or Singapore to Shanghai to Seattle. It's Singapore, Tokyo, Seattle, Singapore, Shanghai, LA. So we're sort of breaking down that node and rewiring the network to ensure that the representation of the data structure in that ways is consistent to what the expectation may be. So this is the invasive species example that we will sort of go through quickly here. As I mentioned earlier, it's about $120 billion a year in damage and control costs. And not to count the the beach going experience that's been affected because of these species in many ways, especially the zebra mussels where they've been clogging water pipes, attaching themselves to boats. So how it's truly creating a damaging effect on the boats. And how this invasive species truly happens is a ship leaves a port. And at that point, let's assume for a second that the cargo isn't full in the ship. The ship is not fully loaded. So what the ship does, at the port, it fills in, it loads in the ballast water. It loads the water into the ballast, so sort of it can compensate for the lack of sufficient cargo in the ship. So it loads up the water, has whatever cargo it has, goes from Shanghai to Singapore. It goes to Singapore, it says, hey, I need to load up more cargo in the ship now. What's the ship gonna do? Get rid of the water it filled in from Shanghai into Singapore port and fill up the cargo. Sounds like, a natural thing to do, right? Water goes into water, right? But along with the ballast, when the ship is sort of loading up the water into the ballast, all the organisms that may be in the port in Shanghai, in that ecosystem, are now getting a free ride to Singapore or beyond. And then when they're being discharged, and if that ecosystem is compatible to them, that ecosystem becomes the new home for those species. And the existing species in that ecosystem go, we didn't expect you here, and how is it going to work out now? And the invasive species begin to quickly dominate that environment from that perspective. So the native species then sort of go through that struggle, and the invasive species multiply, and the ecosystem goes through the shock factor. And all that happened was through the shipping network. And the way folks have been sort of doing these things is, where we look at is, there are policy frameworks where we do ballast water treatment. There are policy frameworks where we may look at how the species may be attaching themselves to the hulls of the boats, not just the ballast. They could be attaching them to the hulls of the boat. Certain species may not even last the voyage. How do we encounter those factors? Certain species may not even, certain ecosystems may be fully inhospitable to another species, so they may not even survive when they reach that ecosystem. But this entire ballast water treatment and the hull aspects, managing the hull, is an expensive procedure. Generally, private companies operate the ports and they operate the ship movements. And it has to be incentivized as to why it makes a good business sense as well to be able to manage the spread of invasive species through the ship as a vector. So how do we now, if we can more accurately model and predict, if we can sort of develop a network approach where we can say, hey, this port, by leveraging the trade data, by leveraging the ecosystem data, by leveraging the climate data, if we can say, hey, this port would not be at risk to this port, if a ship is moving here, don't worry, nothing will survive. But if this port is at risk for this port, then hey, let's do some management. Can we create a hedging scenario for these shipping corporations where now they can balance out their investment towards ballast water treatment from one point to the other? So what is that right policy construct from that perspective as well? And this is where we are beginning to apply our work in collaboration with our biology colleagues, with our economics colleagues, with our policy and engineer turned into a policymaker to understand what is the right construct of taking these models and giving it to policymakers to make this effect. And this is becoming even more compelling now as we think about the Arctic, where the Arctic is being opened for ship voyages to happen. It was pristine. It was a very closed network. Even if any traffic that happened within the ports within the Arctic. And now that's going to open up to the other ports in the world. What is the risk that exists to the Arctic ports from which other ports? Yes, the voyage to the Arctic may save us on time and distance, which may save on fuel, which may save on emissions, but what other risk it may pose from an environmental perspective. So can we begin to do that? And in fact, we are working with a Canadian group who have a base in the Arctic, and they sort of collect water samples from different ports, and we are sort of doing eDNA analysis to see what kind of species currently exist, what the species bank is, what kind of risks may be from other species if they are not found, what kind of ecosystem parameters there may be, and can we begin to arrest for these conditions preemptively or wait for $120 billion, the Great Lakes disaster with Zebra mussels and Asian carp that we have in the United States and Canada. So, so to give you an example as to how the higher order networks have been really useful is, so we used the first order networks. In fact, when we first published our work in KDD a couple of years ago, we used the first order network, and we were really excited about, hey, how we can leverage network science to make these predictions and to leverage these networks. And we used these first order networks, and we created these clusters, etc. And we said, hey, we can now create clusters, zones of groups, and we were excited. 2 years later, or a year later, we realized how wrong we were. But hey, we got the paper in. Not that the paper was wrong, but how wrong we were in our thinking at that time, where these are actually higher order dependencies. And just to give you an idea, once we look at the higher order, in the first order, Valletta and Malta Freeport are in the same cluster, and they should not be. The reason being, Valletta is an inland port, where it's mostly traffic within the region. Malta is a free port, international port, where it's getting traffic from different places in the world. They really cannot be in the same cluster. Their risk exposure is not the same. Even though geographically they should be in the same cluster. But from from an invasive species risk perspective, they should not be, because we should be looking at higher order dependencies. When we didn't look at that, when we only looked at which was the previous port coming to Malta or Valletta were very similar. But if I go beyond, Valletta falls off the chart. It has no traffic going beyond the first order. So we sort of looked at that, and this was a very interesting observation, including to our biology colleagues who were collecting this eDNA species data, and they said, this makes really good sense now. So now we are sort of writing another paper, which we hope would get into a high-profile journal, where we are looking at biological implications of these observations. To quickly sort of talk about is we also applied, I've been given my 5-minute warning now. 20 minutes seemed like a lot of time, but not so much. Where we looked at the first order and higher order network, and sort of if you think about the actions that I may take on clickstream data. I view photo, I upload photo, I go to the home page, and it's not happening that way. I go through different steps when I go to a website. I may upload my photo, I go to a different page, I may go to a different page, and when I find the information I was looking for, or find the place I should be stopping, I stop then. But I go through that sequence of steps. And by using higher order, we showed that a large number of 26% of pages show more than 10% changes in ranking, and more than 90% of pages lose their page rank scores, while a few pages gain their significant scores. So basically, if you look at the higher order networks, the importance of web pages, the importance of pages within a site or links within a site begins to decline as well. And then we have also been looking at it from anomaly detection, just to give you a simulation work. This work is under review as well right now, where if we look at different timestamps of trajectories, phase 1, phase 2, we construct the first order, we construct the higher order, they look identical right now. There is no change, but suddenly when there is a second order pattern that begins to emerge, first order misses it, it says, hey, there is no difference, higher order network captures it. Now imagine if the anomalies, if an adversary was trying to play with your network, and at phase 3, injects certain things. A first order network would basically be fooled and said, oh, yep, nothing has changed. But the higher order network would say, hang on, things are splitting now. I am seeing a higher order occurrence in my data, which I didn't see before. So we can sort of begin to look at and compute graph at the distances and see how things change. So what we have also developed is, as I talked about, is a visualization and interactive framework. We sort of have, and the higher order network entire software is open source, publicly available, but we'll also be making this visualization interface publicly available as well, where we have geographical view, dynamic view, subgraph view, aggregation view, and a table view. So we can sort of create and select different aspects of the higher order networks. So for example, in looking at this visualization, I can look at different ports. I can look at where they traveled from. I can zoom into that port and see what the movement was, where it was coming in from. So I can truly begin to see how the diffusion patterns are happening through a subgraph expansion by focusing on certain nodes of interest. by focusing on how some of these things maybe come into being. And we are applying it to a wide variety of data, from human interactions, human behavior, even on healthcare. We're looking at disease trajectories now, how diseases, transportation data, even NLP. Can we look, are there higher orders that exist in the occurrence of words, etc., within the text framework as well? So again, just to summarize, we came up with HON first, and then we said, hey, HON plus could be more, but we had our pain point was that we really needed a parameter user-defined stopping criterion, and then we got rid of that in HON plus. We have applied it for clustering, ranking, and anomaly detection from various perspectives, and we also now have a significant framework to visualize and interact with these higher order networks. And again, you can, this is the website, higherordernetwork.com. You can download the papers, download the software, we can't make the shipping data available due to the terms and conditions, but everything else that we have used is available from that perspective. But we can tell you how to get the shipping data. Lloyd's Maritime Insurance Unit leases it for a good dollar amount, and one can procure it. And I'd like to acknowledge the folks who have funded us on this research: ARL, NSF, Network Science CTA, and I can take questions now. Thank you.